Hey, my name is Manish Gupta, and in this video, I'm going to talk about LLMLingua, which is a way of compressing prompts for accelerated inference from large language models. So let's get started. How does LLMLingua compress prompts? Okay, so what you see on the right side are these original prompts, and then you see this LLMLingua box. It's basically going to use some large language model. But then to use that large language model, rather than using this original prompt, it basically gives this compressed prompt, which is basically used to get responses from the large language models. Okay. Now, to be able to do this, LLMLingua actually consists of three different components: budget controller, iterative token level prompt compression, and also distribution alignment. And I'll talk about those three components in detail on this slide. Okay. Of course, it also makes use of some small language model. Okay. So, in general, a prompt to a large language model comprises of three things: instruction, a few short demonstration examples, and the question, and the last question, the main question, right? Uh, Now, a simple way of compressing these prompts is called as selective context. The idea is that a prompt contains many sentences or tokens or phrases, whichever unit you want to consider. And then what you could do is to really remove those particular tokens which have very low perplexity, right? So those tokens which have low perplexity or high probability of being sampled from the language model, those are redundant tokens. You can remove them, right? However, removing them using the large language model itself is very expensive. And therefore, what people have done is to really use some small language model to remove those tokens. However, again, the other problem is that the small language model may not be very aligned with the large language model, which basically means that even though the perplexity is very low thanks to small language model, it may not be low for the large language model. And therefore, amongst the three components in LLMLingua, you have this third component, which is basically taking care of this distributional misalignment between the small language model and large language model. It basically ensures that if you have to compute perplexity and remove tokens based on perplexity, you would use a small language model. But then this small language model is instruction tuned using data generated by the large language model, so as to essentially be distributionally aligned with the large language model. Yeah. Now, now the broad idea is to still sort of reduce the size of the prompt using perplexity. However, this is done in two important steps. A broad level step using budget controller and a more fine-grained step using token level iterative compression. Okay. In this broad level step, the idea is to basically compress demonstration examples as much as possible. Okay. So remember, in the prompt, the instruction is super important. The question is super important. There could be too many demonstration examples, and you may want to get rid of a few of those redundant ones. Okay. So the way you would do this is to basically predefine the compression rate for instructions and questions. So you would say that, hey, instructions and questions, this is the rate, and I'm not going to compress more than that. Okay. And that tells you the overall budget for demonstration examples, that, hey, these are the number of tokens that I have for demonstration examples. And then what you do is to basically use this SLM, this SLM that you have instruction tuned using data from LLMs. So as to essentially compute the perplexity of each demonstration example. And then the next step is obvious. You will only retain high perplexity demonstration examples, which lie within this budget that you have computed for the demonstration examples. So that's the broad level budget controller, which gets rid of a few demonstration examples which have high perplexity. Okay. Which have low perplexity, right? So that's that. Now, the next step is to basically do fine-grained, prompt compression by deleting tokens. Okay. So the way you do this is to basically take the prompt that you have obtained from the first step and divide it into several segments. You cut it down into several chunks or segments. For each segment, you're going to do three steps. The first step is to, of course, use the SLM to compute the conditional probability and the perplexity of that segment, right? And then by looking at the perplexity of all the segments, you can actually decide looking at that perplexity distribution, you can decide the perplexity threshold for each segment. So you say that for each segment, this is the perplexity threshold, which defines in general the budget that you can allocate to that segment in that senses. Okay. well, there is no specific controlled budget, but based on the perplexity of the tokens in that segment, you're going to get rid of the low perplexity tokens, and that gives you your reduced segment, which you keep concatenating to the final prompt, thereby obtaining the final prompt at the end. Note that this is done iteratively, such that when you're computing this conditional probability for any segment and the tokens in that segment, it's basically conditioned on the compressed previous segments. Yeah, that's how LLMLingua works. Okay, so how does it perform? Well, they compute the performance, or they try to experiment on 4 different datasets: ShareGPT, Archive, March 23, GSM 8K, and Big Bench Hard. Okay, so these 4 are very popular benchmarks, and they report various metrics. So for ShareGPT, they report Blue, Rouge 1, Rouge 2, Rougel, and so on. So, for GSM 8K, they report exact match. Big Bench Hard, again, they report the exact match accuracy metric. Okay, so the obvious thinking is that if you basically compress the prompt, you expect the model accuracy to reduce, right? To reduce. They of course also report the F1 and so on here, right? So and they sort of compute these sort of so they compute the trade-off between the reduction in the size versus the reduction in the accuracy as you compress the prompt. Okay? And the comparison is done against 3 different baselines. The first baseline is, of course, selective context, where you basically just get rid of tokens based on their overall global perplexity, right? The other comparison is done using the GPT-4 generation. So you could actually tell GPT-4, here is the original prompt. Can you basically compress it down? Okay. So in fact, they do it using 10 different sets of instructions. 3 of them are shown here. Those are in the paper. So could you please rephrase the paragraph to make it short and keep 5% tokens, right? That's how you can actually ask GPT-4 to compress the original prompt also. Okay. So, and then the third baseline is the sentence selection baseline. You randomly select demonstration examples or randomly select sentences in that sense. Okay. So now, let's look at the ShareGPT results and the Archive March 23 results. They've been reported under 2 constraints, 2x constraint and 3x constraint, where you basically expect the method to sort of reduce the prompt by 2 times or 3 times. And similarly, you can also report the results using 350 tokens or 175 tokens constraint, basically saying that, hey, you can put up a constraint on the exact number of tokens, basically ensuring that the models don't generate more than the provided constraint. Okay. So as you observe, sentence selection and selective context are good, but they are not as good as the method LLMLingua, which is proposed in this paper. Right? So as you observe, several times you observe that the results obtained, the accuracy metrics that are obtained using LLMLingua are better compared to other methods, while the compression is guaranteed. While there is about, for example, in this Archive March 23 dataset, using LLMLingua, you can actually obtain a 9x reduced prompt, 9 times reduced prompt, with pretty good, reasonable results, Okay. Now the results on GSM 8K and Big Bench Hard are shown on the right side. And they are shown around different kinds of constraints, like one-shot constraint, just having one demonstration example, half-shot, reduce the demonstration examples by half, or quarter-shot, reduce the demonstration examples to a quarter of the original set of examples. Okay, so there are also these zero-shot and simple prompt results which are reported, and as you observe, again, LLMLingua gives you really good results along with good compression as well. Good results along with good compression as well. Okay. So for these particular experiments, they experimented with the GPT 3.5 Turbo as the large language model and the Alpaca 7 billion as the small language model. Okay. So here is a case study on how this prompt compression works. So this is the original prompt that is shown on the left top, right? So as you see, it's pretty long, and it's a math reasoning kind of a question. Okay. It's not the full prompt that is shown. Of course, there's a query as well, right? But this basically shows you an example, a demonstration example. And this is how the demonstration example looks like after compressing. So as you observe, several of those tokens are reduced. So highlighter basically becomes highlight, high L, right? And then you observe, rearranged basically becomes something like that. So it sort of becomes unreadable. This question guy just gets dropped, right? 3 ters. Now that's basically, it's coming from some token. It's sort of difficult to correlate, but in general, the idea is that yeah, 3 from here and some ters from there and so on. So it's sort of difficult to read this reduced prompt, but it works. It works for the LLM. Okay? LLM can make sense out of it. Okay. So the same compressed prompt from the previous slide. And now if you ask this question, this is the actual question in the prompt, right? This is the reference answer, which nicely gets you 694 as the answer with the original prompt. Okay. However, if you use the compressed prompt, you get the reference answer like that, and it's a correct answer, fortunately. The prompt compressed by LLMLingua. However, on the other hand, if you use this baseline selective context, it compresses the prompt, but on the other hand, gives you a wrong answer, which is bad. So thereby, this example just shows how LLMLingua can actually compress the prompt nicely while retaining the accuracy of the math reasoning task. Okay. Now, an interesting question to ask is that, hey, if I basically took the original prompt and compressed it down to that, can I sort of use a large language model like GPT-4 and tell it, hey, here is a compressed prompt, give me the original prompt back again? Now, it turns out that yes, you can recover the original prompts which has been compressed by LLMLingua using GPT-4. So it turns out that the large language model somehow has this information of refilling those redundant tokens. And it basically gives you the original example back with the correct answer. Okay, so in summary, in this video, I talked about LLMLingua prompt compression method, which comprises of 3 important modules: budget controller, iterative token level compression, and distribution alignment. They experimented with 4 different datasets: GSM, 8K, BBH, ShareGPT, and Archive March 2023, and showed that you can obtain 20x compression in prompts with just a 1.5 point performance drop. And lastly, they also showed that large language models can effectively restore those compressed prompts as well, which are otherwise not human readable. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.